procedures for what matched. So when we had real part and a polar number, we had a procedure called real part polar. When we had an imaginary part for a polar number, we had imag part polar. Similarly, magnitude polar and angle polar. And then we had similar procedures over here. Real part rectangular, imag part rectangular, magnitude rectangular, and angle rectangular. So if we had a table like this, then what we could do is we could say, well, let's look up. I want to get the real part. This would be the operation that I want to do. And this would be the type that I wanted to perform the operation on. So we could look up my operation if I want a real part, and my type is that I've got a rectangular number. I would pull out the real part rectangular procedure. Okay. So how do we know, if you remember from last Friday, how did we know if we had a polar or a rectangular number? It had a tag, had a type tag. Now, do you guys remember these routines here, these procedures, would they pass the data with the type tag on it or the type tag off of it? Off of it, right? Because when we call these, we already know what kind of data we have. So we have a table, we get the operator we want, we send the tag, but the tag is stripped off at that point. So these are not going to use the tags inside the table. So to put things into the table, we have a procedure called put. And you put the operator, the type, and then whatever item you want to have in that slot of the table. So let's say we wanted to install real part rectangular as our real part type rectangular. We would write put, quote, real part, quote, rectangular, and then we would put in the procedure real part rectangular.
Is this a scheme function?
It's actually one that's built on top of scheme. Okay, so we're going to talk today about this table. We're going to talk about how to use a table, how to put stuff in using put, how to pull stuff out using a get command. But we're actually not going to talk about how the table's constructed, because you guys actually haven't learned enough scheme constructs yet to actually understand how the table itself is built. When we get to section 333, I believe it is, then we'll be able to understand how the table is actually built. But for now, if I tell you that put does this, and I give you the corresponding get, then you're going to know everything you need to do the problem set. Okay? If you're interested in seeing the code, one of the files loaded will be called put-get.scheme. You don't need to understand this code. If you just want to look at it to see what the table code looks like, you feel free to. You're probably not going to be able to understand it at this point. We haven't learned enough. Okay, but that's where the code is.
Do you have to make a table before you use put?
All that stuff is going to be handled for you automatically. So all you have to do is just say put the operator and the type, and it's all going to happen for you guys automatically. The table's going to be there. You guys are going to be able to add to it. Okay, so this is one of these things where we're going to do some abstraction. We're just going to tell you you have a table. I'm going to tell you how to put stuff in and get stuff out, sort of like a constructor and a selector, and just tell you to use it. And let's not try to understand the understanding mechanism right now. We'll get to that in a little while. Okay. So we also have get. And get takes an operator and a type, and it returns the item that was put in that slot of the table. So if we wanted to, if we knew that we were trying to get the real part and we knew we had a rectangular number, we would write get real part rectangular. Okay? And that would return to us the procedure real part rectangular. Okay, so this is how we put stuff in, and this is how we get stuff out. We're going to have one more piece, a way that we can actually apply a generic procedure. These operators here, real part, imaged part, magnitude, angle, we could refer to as generic operators. Okay, so what we want to be able to do is have the user say angle and then some complex number. And have it go off and do the right thing. Okay, so that it becomes a little clearer, we just say we want the angle, the some complex number, and all of the dispatching is going to be handled by our table, by the put and the get.
And it doesn't matter whether we're using rectangular coordinates or polar?
No, because let me show you what apply generic is going to look like. So we're going to have a procedure called apply generic. And this is in the types.scheme file you guys have in front of you. So we're going to have a procedure called apply generic. And it's going to take two things. An operator, and now we're going to see that dotted notation again. Op.args. Okay. So recall, we talked about this very briefly in, I think it was Friday's lecture. Any parameters before the dot you have to have. Okay. So if we have one, it means we need to call apply generic with at least one parameter. Anything after the dot means that we've got some optional number of arguments that we're passing in, which could be 0, 5, 10, 500. And what scheme will do is it'll match one for one if we called apply generic. This isn't going to make much sense to call apply generic with a number as an operator, but let me just do this for the sake of, here, we'll just make this list. Okay, so what a scheme does, it says, okay, I'm going to match op to list, and then I'm going to match the rest, anything after the dot, to args. And args will be set to be the list 2, 3, 4, 5. Okay, yes?
Can you say again what apply generic, what are you defining here?
I'm defining a procedure apply generic, which is going to allow us to take a generic operator and apply it to some arguments, and that'll go off and call the table for us. We haven't, I just wanted to talk about the dotted notation before we finished going into apply generic.
The dot has a space on either side.
Yes. Because it's an operator.
So is that going to give you a list of a list?
Well, it depends. Okay, so what happens is we get these args, and then we need to do something with them. So we're going to see in apply generic that we're going to map something over the list that we get. Okay, so we have.
Operator in op doesn't automatically apply itself.
No, it doesn't automatically apply. Let's actually look at the code of apply generic. So the first thing that happens when we go into generic is we want to find out what type our arguments are. Okay, so we've got an operator, and now I want to know what types are they. What am I going to be operating on? Am I going to be adding two numbers? Am I going to be adding two rationals? Am I trying to get the real part of a polar or a real part of a rectangular? I need to find my type. So I'm going to have a let. And I'm going to let a variable called type tags be the result of mapping the selector type tag to the list of arguments. Okay, so let's say we called apply generic real part, and then I had some number which was rectangular with 3.4. Okay, so if you recall, the structure of a number was rectangular, and that was consed onto a const cell like that, which would print out this way. So if we call apply generic on the real part with this number, this goes in as the operator, and then scheme makes a list of that. So args is going to be rectangular 3.4. Okay, so it's a list of this list. Yes.
I'm confused why it seems like today we've gone to using symbols, whereas before all the things that are arguments to get and put, you're writing them with the quote beforehand, and we, up to this point, most of our arguments have been without the quote. Why are we now using the quote?
Because when we go to pull out of the table, this needs to be a symbol. But what we would do in order to use this, which I was going to get to later, is we'll define real part of x. Actually, we should call it z. And then here we would pass z. Okay, so we put a wrapper around it. So our user won't actually be writing this code. Okay, let me finish writing apply generic, and we'll see where that operator comes in and why we need to pass it as a symbol.
What is type? That let tag or type tag map type tag? That's not actually tagging the complex number, is it?
No, it's pulling the type tags off. So we have a selector called type tag, which is at the top of your code for types.scheme. And we'll get some more space. So they define type tag of some datum to check to see if we've got a pair because if we don't have a pair, we haven't const a tag on, right? We've just got some number. We haven't const a tag on. And if we do have a pair, we're going to take the car of it. That'll be our tag. Otherwise, we're going to return an error bad type datum. Type tag. And then return the argument. Okay. So this is our selector type tag.
So all it does is error check, right?
Well, what type tag does, I mean, it does two things. It's going to pull out the car if we've got, so basically if we had this structure over here that we passed it, rectangular 3.4, it would return rectangular. Similarly, we're going to have another selector called contents. Datum. It's going to look a lot like this, or it's going to look a lot different. Except it's the cutter, right? So it's going to be if pair question mark datum Putter of the datum. Otherwise, error, blah, 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 blah.
So if there's two numbers in ours, it'll return a list of two type tags.
Exactly. So,
Are you lacking a dot in your applied generic?
no, the dot only needs to come in here. Okay, this is where Scheme is going to take what we're passing, our evaluated parameters being passed in here, and Scheme will do the matching here. We don't need the dot here because the dot's already here. Scheme is just going to do a one-for-one match on anything before the dot, and then whatever's left, it's going to make a list of it and put it into the variable here. And if there's nothing, it'll put the empty list in there, or a nil. Okay, so we only need the dot in one place. Okay, so what this is doing is we're going to have type tags is going to be a list of the tags. So if we're only passing in one argument, it'll be a list of one tag. If we were passing in two, it would be a list of two tags, etc. Now that we have the type tags, what we're going to do is we're going to look up to see what the procedure in the table is. In the way, how do we look something up in the table? Get. So we're going to let the procedure be the result of getting op with the type tags. Okay.
Wait, does get work with multiple type tags?
Yeah, actually, so this would need to be a list here. So get, well, basically, if you think about the table, we had built a table that only had one type at the top. In our generic operator system that we're going to create for this current problem set, we're going to have types like number, number, and then for the operator add, we're going to install plus number. For sub, actually I think it's called add number. Sub number. And then we'll have types rational, rational, and we're going to have add rational, sub rational, etc. Okay, so our types can take the form of a list. Our types can take the form of a list. So in this case, type tags will return a list of the arguments. If we had passed in two numbers, we would get a list number, number, and that's what we would pass in to look in our table. Okay. Let me finish up this procedure. So if okay, if we have a procedure we're going to apply it to the contents. We're going to map our contents procedure on our arguments. Okay. I haven't really talked about apply. We're going to talk about this a lot more when we get to metacircularity next week. What you need to know for now is apply will take this procedure that we've looked up and apply it to a list of arguments.
Can't we just map?
Hmm?
Why can't we just map? Not prompt to map contents.
Because it's a symbol, we're looking it up, and then we're applying it over.
When did we define apply?
We could do map, though. We haven't done apply, that's what I'm saying. We haven't done apply.
This takes multiple arguments to the same.
So apply basically takes a procedure and a list of arguments and applies the first to the list. It's like map, and sometimes we haven't talked about apply. We're going to talk about apply in gory detail next week. Unfortunately, this is one of those problem sets where we're using things that you guys haven't seen a lot yet. So this is one of those things that you're going to accept. It's going to work. Sort of a Zen thing. It's there. It's believe that apply is going to take a procedure and it's going to basically apply that procedure to whatever list of arguments we have.
Gives you a list of results.
No, it won't give you a list of results. It will give you a result. Yeah. It takes... It's, if you can think of it, so basically it's not like map, because map is going to return a list of results. What this is going to do is it's going to take a procedure and a list of arguments, and somehow it'll break up the list of arguments, map them into the parameters for each of the ones that we need for the procedure, and it'll then apply the body of the lambda expression. So that's what apply is going to do for us.
Like
Do we extract?
Generates its own.
proc, like if get tags have resulted in this plus.
Right.
So proc is plus, but it's the symbol plus. So you can't actually just say proc max.
But is the symbol plus, or did it actually extract the
It's actually extracting the procedure. It's not the
procedure
symbol.
from the table?
Because when we put stuff into the table, we don't actually quote this.
Oh, never mind.
Otherwise, we're going to have some error. Okay, so what's the take-home message? The take-home message, this is what you guys need to understand for the problem set. We're going to go more into apply in a while. What you guys need to know, that apply generic is going to be passed some operator, some generic operator. In the system that you guys will be looking at, they'll be called add, mul, sub, div, EQU question mark. Those are going to be our generic operators. So it's going to take a generic operator and then some arguments. It's going to strip the tags off to find out if we have a way to deal with the types we passed it. Because we may not have entries in our table. What if we passed it a number and a rational? Well, if there's a missing entry here in the table, we're not going to be able to do anything with it. So we'll get the tags. We're going to look to see if there's something in the table, and that's what we're checking here. If we get something back, then we'll apply it. Otherwise, we're going to return an error. So our table may not be complete. We may not have everything there. So this is going to handle that error checking for us.
But we can redefine numbers as rationals.
But you could coerce numbers into rationals, and in fact, that's part of the problem set. So the question was, if we have a number, and in our system, a number is going to look like this. That's going to be the number 2. It'll be 2 with a tag in front of it that says number. Well, somehow we could turn this into a rational that looked like number 2, number 1. Okay, and that's going to be exercise 5, 6, 7, one of the exercises. Okay. Actually, while we're here talking about this exercise, I didn't put a rational tag on this. Okay. If we were turning a number strictly over to a rational, you would put a tag here. For that exercise, you need to think about where you are in the table. If we're already starting to be somewhere in here, we don't want to put on this tag. Right? Because everything that we're operating on here, these have had their outer tags stripped off. So if we start to put more tags on, we're going to have some trouble there. This is going to make a lot more sense when you've gone through the problem set and you get to that problem, then you're going to go, that's what she was talking about. Okay?
Rational numbers then wouldn't still have a number tag. I mean, you wouldn't still have a number tag on it either. It would just be the pair 2, 1.
No.
Somehow you knew it was rational.
No, because in our generic arithmetic system, what we're going to do is we're going to allow it to make rationals of numbers, or we can make rationals of polynomials, or we can make rationals of rationals. So we want to have the sub-pieces tagged, but we don't want to have the first tag on saying that it's a rational. Okay. Because then what's going to happen is within these procedures, we'll use the generic operators again. And those will strip these tags off here.
Proc
Mhm.
is get,
Get is going to return false if it doesn't have something
but it's
there.
going to return a single proc, even if there's multiple type tags that you're getting off.
It's going to return a single prop because it's going to be looking for this operator. Let's say we were looking for add rational rational. So we'd call it with add. This would be our list type tags. And it would look into that slot of the table and return that.
Okay, so at this point, we're still assuming that even though type tags is a list, that it refers to a single key on our table. In other words, it's not like rational number or rational number or something.
It's a list, and we can index our table by anything. We could index it by single symbols, or we could index it by lists of symbols. In this case, we'll be indexing by lists of symbols.
But the list that is in type tags is just one index. It
Yes,
could be a
right.
list if that's-
So if it's a list that says number, that's it. That's the
You
index.
wouldn't want to see number, rational. That's like saying,
Well, you might have some operator, but that would if we had something where we had a list like that, then we would need to have another entry on our table that said number,
rational.
We
number
already have number
rational. Well, but the question was, what if we had something with 3 arguments?
Okay.
Okay, then we would need another slot in our table for that.
So it's not a list in order to mix categories. It's a list because our categories are named as lists.
Right. You could think of it when we type. In fact, we could have a type that just said it took a single number in, or it could take a single rational in. Or in the case of our polar or rectangular representation, we could have an entry with the list polar. Okay, so we're just representing them as lists so that we can write operators that take 1 argument, 2 arguments, 3 arguments. We'll strip off the tags, and then we'll put those at the top. Okay, so that's just how that slot is marked by a list of tags. It's not going to break it out into a 3rd dimension or a 4th dimension of a table or anything like that. Yes?
Could you just walk through an example of calling applied generic?
Sure. Let's actually write something. Let's look at, if you look at page 1 of generic.scheme, they've defined add xy to be the result of apply generic on add xy. Okay? So this is what they defined add to be. So if we say add and we pass in 2 things, it's going to call apply generic. So let's define a couple of numbers. Let's define n1, the number, to be create number 1. The generic number package is on page 2 of the handout. Those 2 pages. So the first page is where they defined add. The second page, you'll see create number defined at the bottom of the page, where you define create number x. It's going to attach the tag number to what we pass in this case, 1. So this is going to be n1. Let's find a second. Let's just add n1 twice. So this is our number that we've created. So now we could call
Attach it list style, or it just conjures it?
attach tag. If you look at, where is attach tag? I believe attach tag is in, it's going to be cons. I don't know exactly.
That's right. It's the very first thing in the
First thing.
very first thing in the type.
First line types. Okay, define attach tag cons. So attach tag is going to cons the tag on to the number. All right, so let's call add n1 N1. We'll add the number to itself. So we're going to add two numbers. So we evaluate these two. That's number const with 1, number const with 1, and add is a procedure. Well, it's over here. It's a procedure that takes in two arguments, x and y, and then calls apply generic. So now we're going to apply this to those two arguments. So now, you see add x and y, we're going to apply generic. Add to x and y. So this is x, this is y. Okay, so now we call apply generic.
So that's a list of those two.
No, at this point, it's still x and y separate.
Well, apply generic doesn't have the dot. No, it does have the dot.
Apply generic has a dot, but when we call it, we don't need to put that dot there.
That's the call.
So we've been using dotted procedures, or procedures with dot arguments, because we've been using plus. And plus can take 1, 2, 3, 4, 10, any number that we want to put in it. So we've already been using that, but because the dot is only in the definition, it's been transparent to us. And that's what you'd like it to be, right? You don't want to require your user, when adding, to have to put a dot in after the second number or the first number. Okay, so the dot only comes in the definition, not when we're actually going to apply it. When we call it here. Okay, so now we call apply generic number, number. So here we go. When we call apply generic, this is going to be op. And these are going to be made into a list. Number dot 1. Now in this case, the dot is the cons. It's not the dot up there. This is the cons dot. It's a different dot. Looks like the same dot, but it's different. That's dot sub cons. You just can't see it. It's so small. All right, not funny. Okay, so this is going to be args. Yes, arg. Alrighty, so now we're in apply generic. This is our op. These are our args in a list. And the first thing we do is we're going to let type tags be the result of mapping type tag, which comes down to being a car if we've got a pair, over our argument list. So what is type tags going to be?
List, number.
The list of number. Because we're going to map it, we look at the first thing in our list, number dot 1, we take its car, chunk. Next element on our list, we look at its car, number, chunk. Okay, so we're going to make a list of our results of mapping the procedure over each of the elements of our list. So our type tags are now number, number. So now we're going to let our procedure be proc is going to be the result of get, what's our op? Add, and our type tags. Number. Okay, so if you're looking at the generic number package here, you'll see on page 2, around the middle of it, there's a comment that says install the number methods in the generic operations. And you'll see that in add and number, it's not actually add number, it's plus number. We installed the procedure plus number. Okay, so we look at the slot add with our list number. This is going to be returned as our procedure. So proc is going to be plus number. Questions on the lookup?
That number is quoted, sort of, right?
It's a list representation inside, yeah. You could think of it as being quoted.
And plus numbers is a procedure.
Is a procedure that's returned. So we return the procedure plus number. So now we check if procedure. Well, it's not false, so it must be true. I'm going to apply the procedure. I'm going to take our procedure. And then we're going to map contents over our arguments. Well, here's our arguments, and contents basically boils down to be cooter. So we're going to take the cooter of this structure, which is 1. Come to the next item in our list, take the cooter of it, 1.
That becomes a list.
That becomes a list also. And this is where apply wins for us. Because what apply does is it takes a procedure and a list of arguments, and apply is going to break those out for us. So now we're going to have plus number 1, 1. So you can think of apply sort of transforming this for us into that.
So, I'm sorry, if you had, say, more arguments than 2,
If you had more arguments than 2, well, would we have even gotten this far if we had more arguments than 2? So let's say we had number, number, number. It depends on whether we have an entry in our table over there. Okay, so if we had an entry for the list number, 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 then we would have been okay. But if we didn't, then we would have gotten an error here. Because we wouldn't have gotten a procedure returned. We would have had false return instead, and we would have errored out here that would have said no method.
And obviously, if we were defining a procedure for number, 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 it would take 3 arguments.
Right.
But what would happen, just out of curiosity, with apply if there are more or less arguments than the procedure takes?
All apply does is going to take a list of arguments, and it could be the empty list. It could be a list of 1 element, 5 elements, 10 elements. It's just going to effectively, we can think of it as now, list for us, like we had called it with just procedure and then these one at a time. It breaks the list up for us.
it's not going to continue to apply further elements if there are too many elements.
Well, actually, if there were too many elements in the list, we actually wouldn't have even gotten here. Right? We could call apply in a situation, certainly, where we mishandled it, and we call something that takes 2 with 3, and that's where we'd hit the error. But in this particular procedure, we never would get to that case because we wouldn't have had anything in our table. But sure, apply isn't going to do any sort of checking on that. If we passed it 4 things and it was only supposed to get 2, we'll get an error at that point.
That's kind of where it's different from the two memory, where it has, because its whole point is to apply a to-art operator to a list of stuff, so it does it from the end out.
Right.
Whereas this one actually has to be, when it's applied, it has to look like an expression that actually works.
Right.
It has to have the right.
Sure. Okay, so now we have plus number 1, 1. Okay, if we look at the top of page 2, we'll see that plus number is defined as taking 2 arguments, x and y. So this will be x, that'll be y, and it returns make number of plus x, y. Okay, so plus 1, 1, which will be 2, and it will return its make number. Anybody want to guess what make number probably does? It tags it. So make number, which is defined just before the install, says to attach the tag number to x. So we attach the tag number to 2, which is going to give us back number 2.
What's the difference between create number and make number?
In this case, none. Okay. What we'll see is if we flip over to let's see. So here And on the second page, you have define, make rational. Let me write these out somewhere. So in this case, we have define, make rational x, which just attaches a tag, rational, just constants a tag on. And then we have define, create rational. And create rational takes in an x and a y. And it makes a rational of the make rat of x and y. Okay, so create rational would be what we would call from the outside land if we wanted to make a rational number. So let's say I wanted to make a rational, I'm going to call the rational 2/3. Then I'm going to call create rational on 2 and 3. So what that's going to do is it's going to call make rat, which is just a cons. It's going to cons my x and y together, and then it's going to call make rational to put the tag onto it. So our 2/3 is going to point to rational 2, 3. What if we had instead mistakenly tried to call make rational? Well, first of all, we can't pass it 2 arguments, right? Make rational expects to be getting a rational number, and all it's going to do is throw the tag on top of it. But the create rational actually includes for us this process of building up the rational and then tagging it. So it's just another level procedure. So this is called by this, but it pastes together the rational for us. So in the case of the number, there's no pasting to be done, right? So when we had create number or make number, we define make number of x to be the attached tag number x, and then we would define create rational create number rather as a call to make number on x. Okay. So we kept the same structure, the same abstraction with our numbers, even though we didn't really need to. Okay, but it's going to make our package clearer to read. So make rational's twin, basically, or analogous procedure is make number. Create rational's analogous procedure is create number. So in this case, they don't look any different, but we write them that way so that we don't break any sort of barriers. And that way our users can call create rational, create number. And it's not, well, if you're using rationals, you need to call create rational. If you're making numbers, then you should call make number, not create number. It just makes it more uniform to do it this way.
But why you didn't do that in this one, right? Create number x is attached tag number.
Sure. And is it the same thing? Will our user know anything different about that?
Okay, I thought you were saying that we shouldn't use it. I wasn't sure if you're saying we should make sure to name it to make them uniform.
We're naming it uniform here. This is the uniform. Create number, create rational. The internals don't make a bit of difference to our user, right?
Yeah.
It doesn't matter if we call another procedure if we just slam the tag on there. It's that to our user we say, if you want to make some type, you call create type. So whether it's create number, create rational, create polynomial, whatever. That's what we call. Yes?
I have two questions. First is, I've noticed the notation of these parentheses, arrow to parentheses above each thing.
Mm-hmm.
And I'm curious if you could explain that. And then the second thing is, it seems, I'm sure we'll get into this later, but is there a built-in library that already comes with schemes so that you have a ton of numbers to work with? Otherwise, it seems like for every number you want to use, you have to build it first before you can even do anything on it.
Okay, so let me answer the second question first. The second question is there some great scheme library of all these numbers that we can be using? And the answer is no. Okay, so this package that we're writing is on top of scheme, right? So in effect, we're simulating generic operators. We're writing a system to do generic operators. Whereas scheme already is doing some stuff like this underneath for us, right? We're just writing something on top of it. So when we're operating on numbers, you actually need to define the number. So you need to define, if you want number 5, define n5, create number 5. There are a few defined for you in the code for the problem set, but you'll need to define some of your own. Type them in and then have numbers to test on. So you can't just test on an ordinary number 2. You actually need to make it a number in our system and then operate on it.
So this isn't so much for its practical thing that we would be able to, as more just kind of...
This is so you guys can see how generic operators could be handled in a system.
I see, okay.
Right? So that we're calling add. We had defined add. And we're going to add on n2, n3. Now, I've gotten a lot of questions from people who used to program in C about, oh, you know, in C we use this great notation where we say what type we have before everything. And here we're actually using it because it's going to be easier for us in our system to see this. But Scheme doesn't actually need to have that because it's got its internal tags that we don't need to represent. But here it's easier for us to see n2, that's a number 2. And we couldn't call it 2 anyway because we're not allowed to redefine what numbers are. Okay. So that was the second question.
Before you erase,
Yes?
if length by number dot 1 in the second line is the number dot 1 of the first.
Explain
Applied
to you.
generic, you said that in applied generic, you said
Yep.
that number dot 1 in the second line was not the same one as number dot 1 in the first line.
No, it's the same number dot 1. What I'm saying is that the dot here, this dot here means cons. This dot here is for optional args, or some unknown number of arguments. That's what I was saying, is that the dots are different. This is a cons dot, both here and here and here and here. Those 4 places, that's just a shorthand for writing number 1. Okay, so that's what the dot meant. That was the difference in the dots. These are exactly the same. It's just that they've been put into lists here. Okay, first question was, what are all these types above the procedures? Or the question wasn't what are the types, but that's what they are. It tells us the type of the function. So if you look, let me see, repnum goes to,
This is in the comments line above.
this is in the comments line above it, yes. Number cross repnum. So repnum is defining the type, something that's tagged with number. Okay, so repnum means something that's tagged as a number. So in this case, it's like saying number, number. And number, number maps to the type that will be returned if I'm doing something on 2 numbers. In this case, is a number. So this is going to be like the scheme number. And then the cross repnum here means then we'll tag it. Okay, so it'll be, when we operate on 2 numbers, we get a scheme number back, but then we need to tag it to return it. So that's what that type is saying. So if we look at another one down here, for negate number, it says rep num goes to number cross rep num. So negate number, as it's telling you, only takes in one number. And it's going to return a number, which will be the negated number, and then it will tag it with number. And then we see another one here for zero number. Rep num bool. Okay, so it's going to take a number, and it's going to return a Boolean. So we're saying the procedure is equal zero number. Okay, so this is going to take in a number and give us back either a true or a false, depending on whether the number is zero or not. So all of these types are used. They're in the comments, so you can see what type is expected by each one. So if we look at the next page on page 3, you'll see that for its adding, subtracting, multiplying, it'll say rep rat goes to rational cross rep rat. So these procedures are taking in two rationals. It's returning the const structure that represents a rational, and then we're putting on the rational tag. That's what that type is saying.
On page 1, you have a notation. Is it the union? Is it generic?
Yep. Yeah, so on page 1 it says generic numbers are equal to number cross rep num, which means we start off with some number and we put on the number tag, union with some rational number that we built up using make rat. Remember, make rat cons is the two pieces of a rational together, crossed with the representation for a rational, in this case our tag rational, union with some representation for a polynomial in our system, crossed with rep poly, or the tag for our polynomials. Okay. And so it defines that because on page 1 it says for add sub mul and div, we have a generic number going to generic number. So this means we've got something that's tagged, and we're returning something that's tagged. And that thing could either be a number, a rational, or a polynomial. Yes? Maybe? Cool. Check. Other questions? It's 11.
I'm just trying to map this in my head, and it seems as though pedagogically one of the points of this is first, in order, we dealt first of all with procedural abstraction, and then we dealt with data abstraction, and now we're dealing with a system which combines both. Is that a useful way to think about it?
Yeah, actually isn't a bad way of thinking about it. So we saw some data abstraction, we saw some procedural abstraction, now we're putting it all together in one big table. Abstraction on top of abstraction. Abstraction is good. We like abstraction.
In the case of complex numbers, it seems like you have a two-layer tag structure. One is to find out, okay, I've got a complex number. Now, am I going into the polar or the rectangular? So do you have to double tag it?
What we would do in that case is we would have an entry in our table for complex, and then we would need to have tags for the next level down when it's stripped off the pieces for polar, or rectangular, or for polar, rectangular, polar. If we wanted to put an extra level of tagging on there, where we represented the complex number package as in here, this would be polar cross rep complex union with rectangular cross rep complex. Okay, that's if we wanted to put another level of tags on for complex. Then once we strip those off, then we would need to operate on the polars, so we'd need to strip off the tags off the polars or off the rectangulars.
So you would have 2 tags.
Right, you might have 2 layers if you were going to build it that way.
And within our procedures for handling these, we would then run the apply generic again
Right,
to pull off.
right, to pull off the
They're
stuff.
separate tables, right?
Uh,
The rectangle.
I mean, it could be all in the same table, right? You wouldn't need to have a separate table. You could just have tables that have, you know, multiple lists of what the types are going off. You don't need to have a separate tag for complex, a separate table. And the table doesn't need to be populated, fully populated. There are certain operators that may not make sense to have on, you know, some types. So the table could have empty slots. Other questions? Okay, why don't you guys go off and start the problem set, and then when you guys go back to recitation, we can talk some more about this stuff.